Look at this review problem. Summation n equals 1 to infinity of 2n plus 1 over n plus 1 quantity squared. We will do this one in two different ways. The first way is certainly the way that I would recommend. Method number one, we use the limit comparison test. Okay, now what should we compare this to? So when we use the limit comparison test, we're going to define limit as n goes to infinity of the original nth term, 2n plus 1 over n plus 1 quantity squared over something. And that something should be something that's fairly straightforward that we understand. All right, so let's take a look at the fraction here, 2n plus 1 over n plus 1 quantity squared. Now, what happens if this is n gets large? As n gets large, 2n is the most important thing in the numerator. On the bottom, n plus 1 is basically n, so n squared. And so that's equal to 2 over n. I notice my friend n to the first power here, which strongly suggests that this is going to diverge. So let's do the limit comparison test with this with 1 over n. I could have done 2 over n. I'll do 1 over n for the sake of the review. 2 over n would have been just fine. This is equal to the limit as n goes to infinity of 2n plus 1 times n over n plus 1 quantity squared, which is the limit as n goes to infinity of 2n squared plus n over n squared plus 2n plus 1. At this point, I could use L'Hopital's rule, but it's a whole lot easier to observe that I've got a polynomial on the top and on the bottom. And so my rule is that I look at the leading terms, n squared on top, n squared on the bottom. And so the answer is going to be 2 divided by 1, the ratio of the coefficients of the leading terms. So this will be 2 over 1, which is equal to 2. And that could have been done by L'Hopital's rule, but I'll use, for the sake of expediency, my rule about rational functions. All right, now the number 2 is not important. What is important is that it's a number between 0 and infinity. So the series involving this and the series involving this either both converge or both diverge. Well, we know that summation 1 over n diverges, and that's a p-series with p is equal to 1. Or I could just simply say that's harmonic series. We conclude that the original series, summation 2n plus 1 over n plus 1 squared, also diverges. So these both converge or both diverge because this answer here is somewhere between 0 and infinity. And in this case, the series involving the denominator diverges, and therefore the series involving the nth term being the numerator also diverges. Okay, so that's method number 1. Method number 2. Now, method number 2 is not recommended, but I am putting it here for review purposes. And the technique for method number 2 is we use the integral test. Okay, so to use the integral test, let's let f of x equal to 2x plus 1 over x plus 1 quantity squared. And I'm only looking at the case where x is greater than or equal to 1. To use the integral test, we need to check 3 things. Number 1, f is positive. Numerator is positive if x is greater than or equal to 1. The denominator is positive if x is greater than or equal to 1. So that is a positive function. Number 2, f is continuous. This is a rational function. As long as I don't have the denominator being equal to 0, which can't happen if x is greater than or equal to 1, there's no problems. And the third thing that I have to show, which is going to take a little bit of effort, is that f is decreasing. Now, the way to establish that this is decreasing is to take the derivative. F prime of x is equal to, all right, let's take the derivative. Derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Okay, now to do this, notice I could multiply out the top, but it's a whole lot easier to factor out an x plus 1. So let's factor out an x plus 1 from the top. What's left will be 2 times x plus 1 minus 2 times x plus 1 times 2. All over x plus 1 to the fourth. All right, what's left? We get x plus 1 to the third on the bottom. On the top, we're going to have 2x minus 4x for negative 2x. And on top, we have 2 minus 2, and that cancels. And clearly, that is less than or equal to 0 if x is greater than or equal to 1. So the top will be negative, the bottom is positive, and so this fraction, the derivative, will be less than 0. And so I've got all three things checked. It's positive, it's continuous, it's decreasing, and therefore I can apply the integral test. So we now examine the integral from 1 to infinity of 2x plus 1 over x plus 1 squared dx. And that's equal to the limit as b goes to infinity of integral from 1 to b of 2x plus 1 over x plus 1 squared dx. Okay, I can apply partial fractions to this to be able to do the integral. However, in this case, it's a little bit easier. Rather than doing the usual way of finding partial fractions, this one is actually pretty straightforward to be able to write it out. This is equal to 2x plus 2 minus 1 over x plus 1 squared dx. So that's the limit as b goes to infinity of integral from 1 to b of 2 times x plus 1 over x plus 1 squared minus 1 over x plus 1 squared dx. Equals the limit as b goes to infinity of integral from 1 to b of 2 over x plus 1 minus 1 over x plus 1 squared dx. Okay, now at this point, we just do the integral. Now, this can be done by u substitution. Hopefully, by this point, you can actually just see what the integral is going to be. This is going to be 2 times the natural log of absolute value b plus 1 plus 1 over b plus 1, or actually, sorry, x plus 1, not b plus 1. Evaluated from b to 1. And I did it again. That's equal to the limit as b goes to infinity of that expression. So the limit as b goes to infinity of 2 times the natural log of b plus 1, and I can get rid of the absolute value signs because b is positive, plus 1 over b plus 1 minus 2 times the natural log of 2 plus 1/2. Okay, now that is equal to infinity. This blows up. That goes to 0. That's a constant. So this part here is a constant, but this blows up, and so the answer here is going to be infinity. So this integral diverges. By the integral test, if this integral diverges, then the original series diverges as well. So in conclusion, therefore, the original series that we started with at the top of the problem also diverges. Okay, now for this problem, the limit comparison test is certainly the easiest thing to do. For the sake of review and for the sake of review only, I wanted to show that there was a second way of being able to do this. Certainly for the exam, we only expect to do things one way to get the correct answer.